Alright, hello again and welcome back to Garage Science. So this is a different project. So this reflow oven is something I need to make so I can do some surface mount PCB projects, but I'm going to kind of overboard with it just to make sure that it's trying to do it real well. There's lots of videos out there about modifying toaster ovens to do surface mount reflow oven work, and this is my attempt at it. But like I said, I'm going kind of overboard. I got the toaster oven pretty cheap off of Amazon Prime days, along with relays and heat sinks, so still a relatively cheap project. But yeah, it's a little more than I would say most people probably do. So I'm going to go over the gist of it real quick. It's not done yet. This is just a really just the initial test run is the initial wiring is done. So it's a 1800 watt, 15 or 1800 watt toaster oven. It's got heating elements on the top and the bottom. It also has a circulating fan. Its build is being able to do air frying as well as toaster oven stuff. I've basically taken the controller board completely out of the loop. All of the connections for the heating elements are these spade type terminals, so it made it really easy to disconnect everything and rewire it. So basically what I've done is taken the common neutral and obviously taken that to all of the various elements, and then on the power line, this guy here, the incoming power branches off and goes to each of the relays. These are 60 amp solid state relays, and then from there I've got one relay that controls the bottom heating elements, one relay that controls the top heating elements, and then one relay that controls both the fan and the lamp, the internal lamp as well. So all that runs to a Arduino Nano. It's right here. I think you can see here. Yeah. So this Arduino Nano was going to be the brains of the outfit. Off of the Arduino Nano are 4 thermocouples. So I bought these Max 6675 chip boards. So that's a Analog Devices chip, and it's just a simple board that breaks that chip out to the inputs and outputs, and then the thermocouple terminals. I'm using the Adafruit library in Arduino to work with it. It all works pretty well. I'll put links in the description for all these components, so feel free to reference that to buy this stuff. These boards initially came with these thermocouples, and they're listed as being only good for about it's like 150 degrees. It's pretty low, and so obviously I need something a little higher than that to run the toaster oven. And so these thermocouples, I'll pull one out real quick. So these thermocouples, also an Amazon buy, relatively cheap. Link will be in the description. These are supposed to be good up to like 900 degrees, I think, is what the Amazon page said. So overkill for this application, but good, because definitely want this thing to last a long time. I'd like this to be a long-term device that I can use for a lot of different things. So I also added in here a 120 volt plug coming off of the hot and neutral, the incoming hot and neutral, and what that's going to be is a power source for the Arduino. Once it's programmed and it's not plugged into the computer anymore, then we'll use this power brick to power the Arduino. And yeah, so you know, they say like once you do reflow soldering in a toaster oven that you shouldn't use it for cooking anymore, and I don't intend to do that. But there have been no modifications at this point, even though I've ripped everything apart. There's been no permanent modifications to the toaster oven itself. I could actually restore it to its original condition at this point. But yeah, that's where we stand now. I'll go ahead and fire it up. So let me reorient the camera. So the Arduino program is set up right now. So we got power applied to the toaster oven now. So there you go, it just kicks on. So it's set up right now to heat the oven up to 160 degrees and hold it there. And so it's basically waiting for every single thermocouple to read at least 160 degrees. Eventually we'll have them taking averages, so that way you know that the the temperature profile around your PCB is on average a particular temperature. We'll use that to work with the heating profile. And the lamp is actually, it's a halogen lamp, so the lamp by itself is enough to heat the toaster oven up to about 140, 150 degrees. And then the heating elements can heat up after that. So what I'll probably do is set it up so that way there's like an initial soak to get the circuit board up to like 90 or 100 degrees before going through the thermal profile, so you know that there's a common temperature starting point. So there you go. You can see that it's the heating elements are kicking on. Yeah. And the relays are on. You can see their red lights are on. And then your Arduino program is recording the temperatures. And that's not the current serial monitor, so we're gonna close that out. As the old from this morning serial monitor. So now we're updating. So once all the thermocouples are saying 160 degrees, then the heaters will kick off. I think it was 160 degrees. Yeah, there you go. So the heaters are off now. And of course it drifts up past that a little bit because there's a lag with everything. So that's part of the aspects of this project where I'm going to have to actually figure out the temperature characteristics of this oven, so that way you can account for that temperature drift after you cut the heaters off, and the lag associated with the thermocouples, so that way you're actually getting an accurate temperature profile. So this will be a good project. I'm not going to do this as a step-by-step guide. I'll cover the high points as necessary, but this is the initial wiring and setup. It works. Time to make it a lot better and finish it up. So stick around. We'll talk more. Alright, so little update. We're running some tests here, trying to understand how the thermal behavior of this oven is going to work. So you'll notice the oven's on and it's covered in insulation, so I'm trying to heat it up and just kind of see what the maximum heat input or temperature that it can reach is. And so right now we're up to 630 degrees, so it's pretty toasty. I might actually cut it off here in a minute. I didn't expect it to get that high. There is a thermal cutoff switch that I left in the circuit, so if it gets too hot, I don't know what the temperature setting is on that, but the toaster oven itself should cut power if it gets too hot. Is the heat up rate uninsulated right now? I've measured it to be about 0.4 degrees per second. A lot of the literature surrounding no clean solder is that you need a heat up rate of about 2 degrees per second, and that sounds kind of hard to achieve right now. To be perfectly honest. And so I'm kind of working through if I can even get up to that level. So it's about 0.4 degrees per second without insulation. I just measured it earlier. It's about 0.5 degrees and some change with insulation. So I've effectively increased the heat up rate by about 25%, but that's still nowhere near the 2 degrees per second. So there's kind of two approaches to to heating up for a solder thermal profile for solder paste, and one is like a heat up and soak and then ramp to peak temperature, and one is you just ramp straight to peak temperature. And just based off of the heat up rates that I'm able to get, I might just have to do the ramp to peak approach, and the soak would happen basically by nature of it taking so long. So let me know what you guys think in the comments about that. I'm going to go ahead and cut this off. It's we're at 660 degrees, so So peak temperature for this toaster oven gets pretty hot. So the need for a thermocouple is definitely there. I'll try and do some calculations to see what the actual heat transfer rates are. Since I didn't actually reach a peak where your losses are equal to your inputs, it might make that a little difficult, but we'll give it a shot. There's a tiny bit of smoke leaking out of the toaster oven I just noticed, so we'll see how the thermocouple, I think if anything that would be the insulation. See if maybe we can catch some of that. Might be the insulation around the multimeter thermocouple. It's not the metal overbraid, so it might have been getting a little baked in there. But like I said, it's off now. There's no power going to it. We'll unplug it for absolute certainty. The lights for the relays are still on because I'm plugged into the computer for the Arduino, so I can do the data logging. But we're already cooled down to 624 degrees. But yeah, you know, I was kind of hoping to you know, kind of rigorously follow the solder profile. We'll look around and see if there's any downside to just extending the time frame of the solder profile to kind of try and follow it, but over a longer period of time. So I'll do a little research on that, but it's you know, it's coming along. So we'll probably be more to come. I am not, or I still need to do a few things. There's about a 30-degree gradient in temperature across the thermocouples, and that's pretty high considering the thermocouples are only about 6 inches apart from each other. And so I'm a little more concerned about that than I am the heat up rate. So I'll do a few things to try and even out the temperature measurement across the thermocouples. But yeah, we're getting along. So more updates to come. All right, so we are a day later on this, and I ran the heat up profile like described in the last clip, and took all the numbers, plugged it into Excel. I'll toss that graph up. But basically, after putting the insulation on, this 1-inch thick, like oven, you know, high temperature ceramic fiber insulation, you'd think that would help keep the heat inside and allow your heat up rate to go up, and it didn't. It actually went down. And so you guys can go ahead and gnaw on that for now, like how that's possible. But I have some theories. Right, and I'll talk about it at the end of the video. I won't delve into it now. It's because it gets into some heat transfer theory. But we're gonna do an experiment and just do one set of heaters. So we're only gonna do the top 2, I think, heaters. I'll disable the bottom 2 heaters, and I'm expecting that somewhere in the like 250, 300 degree range, the heat up rate is going to stagnate at about 0.1 to 0.2 degrees. And so we'll see if that happens. So if I'm right about why the heat up rate went down, then basically I think the heat up rate should get really slow on 2 heaters around about the 200 to 300 degree range, or 250 to 300 degree range. So we'll see if that happens. Alright, so we did the heat up at 200 degrees, so it's actually still pretty warm in there right now. It does take a while for the temperature to cool off, and we didn't actually get up to 500 degrees. So after 800 seconds, so that's about 13 minutes, a little over 13 minutes, we only got up to 400 degrees. So the time between 800 and 600, basically the average heat up rate was about 0.2 degrees Fahrenheit, and I'll toss the graph up here once I get a chance to put this in Excel. But that's pretty much what I expected. So you know, I'll explain why later, but what I presume is the case is why the heat up rate is going down is because the the insulation is capable of holding so much heat that during the heat up, as much as it's insulating heat from you burning yourself when you touch it, it's also sinking heat out of the toaster oven, and so much so that it's conducting more heat through direct conductive heat transfer than the convective heat loss of having no insulation. So we'll go through why that's the case later, but basically we got to change this up. So this is not going to work. So two things: probably going to pull the case off, and we're going to try and put the insulation inside. We're still going to use the insulation, but there's a fifth heating element in this toaster oven in the top, and I didn't use it because I figured 2 heating elements on the top, 2 heating elements on the bottom, even heat across the toaster oven. That's what I wanted, but sounds like you need that fifth element to boost your heat up rate. And given the theory about the insulation retaining heat and everything, I did the math out for 5 heaters. It does look like we'll be able to get pretty close to the heat up rate that we want if I utilize the fifth heating element. So we got to pull the case off, and we got to wire that heating element so we can use it. But yeah, that's what we're going to do. So we'll put the insulation on the inside so that it's kind of out of the way and doesn't look janky like this. And we'll wire that heating element, and that's the next step. Alright, so got the case cover back off, and unfortunately had to undo my wiring that I spent a lot of time on, but we'll get it back together. So I just unplugged the middle heating element. It has a return wire. Where'd it go? This guy. So these were still plugged into the control board that's not being used anymore. Before I took it apart, so I just unplugged them. We'll feed them through. We'll hook them up to the same relay as the top, as the other 2 heaters on the top, and so all 3 heaters will be controlled on the same relay. The other thing we're going to do is we're going to put that insulation on this wall, and also on the top, and basically all 6 sides. There's a piece we'll keep on the outside for the bottom. Not entirely sure what we'll do for the door, but the top is only about a 1/2 inch gap between that and the casing, and the insulation is 1 inch thick, so we might have to kind of cut it so that way it's a little thinner. But there's a 1 inch gap on this side. There's obviously more than a 1 inch gap on the other side, and then the back has this protrusion back here that we're going to stuff some insulation in there too. So we'll get as much in there as we can, so we don't have tons of insulation on the outside. And we'll probably just call that good enough. So between adding that insulation and adding the 5th heating element, that should get us to the heat up rate that we want. So yep, more to come. Alright, so we've got the insulation packed around the internal firebox basically. So you can see that I did the top side. I have a piece set aside to put underneath it. The back side was a little different in that the back wall is actually the back wall of the firebox. I thought there was another internal wall there, but there wasn't. So I ended up putting the insulation on the outside of the casing. So I think that'll work. I tied it down with some wire. That's what's holding it up there. The tape is just to keep the wire from digging into the insulation over time. So it's because it's on the room side of the insulation, it should never get hot enough to damage the tape. And it's really just kind of being held in there by the wire, because obviously the insulation is going to mess up the adhesive quite a bit. But yeah, that's how we're going to have it. Took a little bit of time to do all the cutouts for the various wires, the hinge on the other side, with the spring, and so you got to put a little time into it, but it's pretty doable. I went ahead and removed the power board from the control side here of the toaster oven, just because it was kind of in the way, and it's not doing anything right now, so I went ahead and just removed it. And then the door has it's basically right now the insulation is wedged in the handle with a little bit of spare insulation that I had, but it holds in there pretty good. I might change how that's done over time, but this door's not going to get opened that much. It can probably sit like that for a while. We're going to go ahead and put the case back on and fire it up. Alright, so the toaster oven's put back together, the wires are redone. That was kind of a pain, but such is life. I've got the multimeter thermocouple set up again. We're going to fire it up and run it up to 500 degrees again. And yeah, there's not much to see when I do that, so that's why I haven't been recording it, just because it's just the oven that gets hot. But you can also see underneath, I've got some insulation underneath, so the bottom's insulated, the front's insulated, there's insulation on the left, on the right, on the top, and so it's very well insulated all around. That fifth heating element right here is wired in with the top heating elements here. So they're sharing the same relay, that's fine. The relays are rated for 60 amps, which is pretty overkill. And then I think I mentioned it before, but I'll mention it again just because took some care and attention to wire this properly. I only had a white hookup wire already on hand for this project, so that's what I've been using. Really, you want to use color-coded wire, and so yeah. Anyways, if you do something like this, probably get color-coded wire. All right, we'll fire it up, and I'll show you guys the graphed results once I'm done. All right, so we're about to fire this up again. The run that I did with the 5 heaters, the difference in the air temperature across the thermocouples was actually lower than during the other runs, and it got to oh, it's not on this paper. With 5 heaters, it actually and with the insulation, really is caused the insulation, but the difference in air temperature across the thermocouples was only about 10 degrees versus the 30 degrees in all the previous cases. And so what I'm going to do is I'm going to see if I can't get that a little closer. And then what you tend to see is the left thermocouple is always colder than the right, which kind of makes sense. The fan's on the right, so it's constantly circulating air. It sucks it in through the center and exhausts it out towards the edges. And so because of that, because there's no barriers, then it's pretty easy to suck in air and then exhaust it and then immediately suck it back in. And so this side of your toaster oven is going to get a lot more circulation than this side. So what we're going to do, or what I have done, is put sheet metal on the top and bottom racks, so that way when the air exhausts towards the bottom, it can't just immediately circulate back up to the middle region and get sucked back in. It has to travel all the way across and then come up at the end and then travel across the center where the PCB will be to get sucked back into the fan again. And so not only will that cause an actual, like, you know, convective circulating flow through the whole toaster oven, but when it exhausts past here, it's going to exhaust past the heating elements and presumably heat that air up, and then come up here and then go across the PCB, providing that convective heat transfer that we're looking for, right? And these aren't like perfectly insulating walls or anything, so they'll radiate heat as well, but it also should protect the PCB from infrared heating. And so the quartz heaters in this don't really get, you know, I don't think they probably produce much infrared light as most of the infrared specific heaters, toaster ovens out there, but they do produce some, obviously, and the sheet metal should actually kind of shield it from some of that. But yeah, we'll see how this goes. I'm not gonna do the temperature profile because we already did that with 5 heaters, and I don't think the little bit of sheet metal here is going to change it that much. But I am going to let it run to 500 degrees and see what the difference in temperature is across the thermocouples. So if I can get it to below 5 degrees across the thermocouples for difference, then I think that's going to be money in the bank. So we're going to fire it up. Alright, so we're heating it up. We're a little over 300 degrees right now, and not sure if it's showing up in the video, but I am getting some smoke coming up out of the top. So presumably that's the plating on the steel plates I added. I mean, I bought this stuff from Home Depot. It just says plated steel. Presumably that's galvanization. Actually, kind of just assumed that it was durable enough to make it through 500-degree heat. But looking online, looks like galvanized plating only is good for about 400 degrees. So I think we're going to end up baking a lot of stuff off here. I think the underlying steel, you know, that'll obviously still be fine. Just gonna be careful with the fumes while I'm heating it up. So it doesn't have to be steel. Maybe I should have got aluminum plating, but that was a little more expensive, so I went without. But looks like I'm paying the price for that now. So if you're gonna do this, maybe get some steel or aluminum sheet metal instead of steel. Well, yeah, we'll see how it goes. Alright, so we're at 500 degrees. The heating elements are still running because the thermocouples are lagging behind. They're saying we're at about 460 right now. So it'll take a second. That's part of the time lag I still have to account for at some point on this. But the smoking's pretty much stopped, so I think there must have been some kind of coating on the top of the steel. Maybe it wasn't the galvanization, but I think I've pretty much cooked it all off. So it's doing fine now. So I'm not gonna consider redoing what I've done. We'll leave it as is. But yeah, make sure the first time you heat up, or any time that you heat up, that you're in the vicinity so you can monitor for things like this. But yeah, we'll get there. Sure, one way or another, we'll get there. So as you can see here, there's a pretty stable temperature between the front, left, and right thermocouples. And they all hang out within about 5 degrees of each other, give or take a couple degrees. But for some reason, the back thermocouple just does not want to be close to the same temperature. And they track similar temperatures at room temperature, but as it heats up, it diverges quite a bit. So I don't think it's necessarily an issue with the thermocouple, although there could be an issue with a thermocouple. I don't know, maybe something just about the airflow right in that pocket in towards the back of the toaster oven. It just doesn't heat up very well at all. So I think we'll probably just eliminate the back thermocouple from the temperature averages so it doesn't obscure it significantly. And yeah, we'll just run with it and kind of ignore that it's there. Shouldn't affect it too much. The left, right, and front thermocouples cover a pretty wide area of the oven area where we're going to have PCB, so I'm pretty confident we'll have an even temperature profile. But if you have any ideas why one of the thermocouples might be off by that much, I mean, some of this is like close to 40 degrees off on some in some instances. So if you have an idea, let me know in the comments. I'd be open ears for any suggestions. Alright, so this is the moment we've all been waiting for. We're going to actually make a PCB. So what I have here, actually if I can get it for the camera. So this is just a breakout board for an 8-pin dual inline package for a MOSFET. So it's a dual MOSFET for N channel, P channel. Kind of just a simple little chip to do a little experimenting with, a little breakout board. I'll put the links in the description. It's actually pretty handy kits, the ones that I got. I'll probably use them for other things in the future, but this will be a good test run. So A couple things that we've done is we've set the maximum temperature goal to be 460 degrees. So that falls in line with the temperature profile for the MG Chemicals solder paste. And then right now I've also set up the oven to do a preheat cycle. So right now it's preheating to 135 degrees. So I just had the door open a second ago, so it's a little bit below that. And so the heaters are cycling on and off to try and maintain 135 degrees. And then what I've also done in order to hit the peak target, because there's a time lag with the thermocouples, just because of the nature of heating them up, the heaters actually cut off about 40 degrees before reaching the final temperature target, and then the temperature coasts up basically to the peak temperature, because the installation actually is able to hold that temperature pretty well. So the Arduino is set to once it cuts off the heaters, to wait a minute, and then it'll set off a buzzer to let you know, hey, your PCB's done. So there's no like cool down forced airflow cycle that I can really inject here without major modifications. So in order to cool down the PCB, you have to open the door and let it cool naturally that way. But anyway, so I usually, when I did this yesterday, I let the PCB sit in the preheat oven temperature for about 10 minutes to acclimate it, and then actually start the temperature profile after that. So I think we're going to do that again and see how this goes. Alright, and so the yellow light lets us know that we're in the preheat mode. When I press the button again, we'll go into heat mode. Well, I'm not going to do that yet. Do that after we sit in preheat for a minute. So I just figured the preheat ought to help make sure that for every PCB you actually start where the entire thing is at some known initial temperature. Consistency's sake, hoping that plays to my benefit. So we'll see. We'll give this about 10 minutes though. Alright, it's been about 10 minutes. PCB's still hanging out in there. We've been sitting at about 135 degrees, so we'll go ahead and get her started, and I'll keep the camera on for the heat up cycle, so you'll see it on the thermocouples as it heats up, but the actual controlling is coming from the other thermocouples, right? So this is just a simple little wire thermocouple for the multimeter. The other larger thermocouples are what's going to the Arduino that is controlling the heaters. So this is just for your own information. But we'll get started. And I'll add a stopwatch so you guys have a sense of the amount of time it takes. Ooh, can't see that on the camera so well. Alright, so you just heard the beeper go off, so that's just the audio notification that we're done. So we're going to let this cool off a little slowly. So it took a little under 10 minutes, just under 10 minutes. And you'll notice, actually, we did get up to 460 degrees, which I had not used that actually to verify that we actually made it up to 460 degrees. When I had tested this before was to get to 450. And that was without the preheat. So I think the preheat actually helps eliminate some of that that drift on the tail end. So anyways, we'll probably edit the Arduino to make it less of a gap So probably reduce that that 40-degree pre-shut off of the heaters to maybe about 20-degree pre-shut off, and yeah, call that good. But we'll see how this board turns out though. So we kind of undershot our temperature goal by about 30 degrees. And you can just ignore that. It's so it's just going to repeat that every minute as a reminder until you reset it. So I probably should have put a reset button on here, but I didn't, and I'm too lazy to reprint all the pieces. Alright, so once this gets down to about 200 degrees, we'll pull the circuit board out. Alright, it's taking a little longer to get that cooled down, so we're going to see if we can't speed it up by opening the door. So the heating elements are off at this point, it's just the light that's on. Alright, that helps speed us up a little bit. Let's pull this tray out. So that can cool down at its leisure. I tend to unplug this just because it's capable of drawing a lot of power, and this isn't exactly UL listed now. So anyway, so I tend to unplug it when I'm done using it. But yeah, let's pull this board off of here and see if we can't ascertain how we did. You can see alright, let's focus in here. Alright, so you can see kind of how it turned out. There we go. So there's definitely some bridging. I think I used a little too much solder, so we'll clean that up with a soldering iron. It's pretty easy. There's if you just run a hot soldering iron across surface mount pins like that, it tends to get rid of the bridging pretty easily. So we'll do that, and yeah, but otherwise turned out very nicely. Very happy with that, and we didn't even hit our temperature goal. So maybe if we had reached the temperature goal we wanted, then we could have gotten the proper reflow on the solder, where maybe we wouldn't have quite as much bridging. But looks like it's still reflowed everything pretty solidly. It's on there, nice and solid, obviously. And yeah, just a tiny bit of bridging we'll get rid of. But that's more my fault than anything. So yeah, it turned out very nice, very, very nice. And here are some additional surface mount MOSFETs on breakout boards that I made up. All turned out very nicely. You can see they're relatively small. I think the pads are only about 1/2 millimeter wide, and they turned out very, very nice. One of the primary projects I was working on was an HDMI converter board. So you can see that here prepped prior to going into the oven. All the solder paste is on all the pads, and now this is the final product. Also worked out very nice, functions properly. This was an additional board, had a lot of capacitors, and it was a power controller board, and worked out very nice. Lots of surface mount components. 100-pin IC is the main component. Looks very nice. All in all, this project took a little longer. It took even longer for me to make this video, but hope you enjoyed it. Make sure you like and subscribe, and let me know in the comments what you think, and let me know if you try and build it yourself. And stick around, because we'll do more and more projects as time goes on. Alright, see you next time.